Hello everyone, welcome to video number 3 on the Gauss-Jordan elimination protocol, procedure, whatever you want. So this is part of chapter 4. We're starting in chapter 4 in the first section. So what we're going to do is a quick overview of the algorithm and then look at some examples with SymPy. Actually solve the exercises. Alright, so what's going on? So imagine you have a system of equations like this one, system of linear equations. So you have some coefficient times x plus coefficient times y equal to a constant and another one of those. So from high school math, you should know a bunch of ways you can subtract these equations, for example. You can do all kinds of manipulations on them to solve. But this happens so often in science that people came up with a systematic procedure for solving this type of equations. So that's what we'll look at today. And it's a bit boring, it's a bit tedious, but it's really powerful stuff. And in fact, we use it throughout the book. We'll use the Gauss-Jordan elimination procedure. So bear with me, this is actually really important. It doesn't look super cool, but it's actually very useful. So the main realization is you can do operations on the system of equations. Like let's say adding this equation to this equation. In fact, we can add a multiple. Let's say alpha times this equation if you add it to this. You don't actually change the equation. The system of equations remains the same. You can also scale any equation. If you double this equation, it's still okay. And you can swap them. You know, right now we say this is the first equation, this is the second. If you change their order, it's allowed, right? Who cares? Just who decided to write this one first. So the Gauss-Jordan elimination procedure starts with a system of equations like this and rewrites it extracting only the coefficients. So instead of writing what the variables are, keeping track what the variables are, we just say the first column here is for the x's, the second column is for the y's, and the third column is for the constants. In fact, it could be a different system of equations with completely different variables. We don't care. It will give it the same augmented matrix. Now, Gauss-Jordan elimination procedure is, we'll take 3 or 4 steps, and we'll convert this system of equations, this augmented matrix, into this form. Now, let's use the mapping back. So we said the first column is for the x's, y is in constant. So what does this read? If we read this as an equation, this says x is equal to 1 and y is equal to 2. So that's how you solve equations, right? You work in this augmented matrix, you simplify it until it gets to this form. So this form where you have 1s on the diagonal and 0s everywhere else, or rather, as much 1s as you can on the diagonal and as much 0s everywhere else, is called the reduced row echelon form. So an augmented matrix, a matrix is in a reduced row echelon form if each column that contains this is called a leading one. It has been subtracted as many times as needed to get 0s all the way below it. And this is not a leading one, this is a leading one in the second column. And it's been subtracted below, and then it's been subtracted from all entries above, so that you get, I mean, it's as simple, basically that's the idea, is to get it as simple as possible. This one too, it's been subtracted from above. Here we don't have a leading one in this column, so we cannot guarantee, like this is still reduced row echelon form, it's just there was no leading one, so we couldn't kill these. This could be any entry here. Same here, there was no leading one. We have 3 leading ones, first, second, and fourth column. And except for these leading ones, in the first, second, and fourth column, we got all 0s. So the Gauss-Jordan elimination procedure takes any matrix and puts it into its reduced row echelon form. So let's look with this example. So what happens here? You have this equation, we write it as follows. In the first stage, we want to zero out this entry here. So how we can do that is subtracting 3 times the first row from the second row. What will happen is you get a 0 here as intended, but this will be so 9 minus 6, 3. 21 minus 15 will be 6. I hope so. I mean, if I didn't make any mistakes, it should be correct. Now here we're done with the first step. Now observe here we have a leading 3. So the algorithm demands that to sort of have a systematic procedure, you want to make this a 1. So that's kind of easy. You divide by 3. So that's another row operation. You divide by 3 here. And then you want to get rid of this 2, so you subtract this row from this row. Because there's 0 here, that column won't change, so you get the final solution. So x is equal to 1, y is equal to 2. I won't go into too much details, but let's just define what you're allowed to do. There are 3 types of row operations you can do as part of the... so you can add a multiple of any row to another row. So that's like if the 2 equations are true, then adding 1 equation to the next is allowed. You can swap the 2 rows, first row with second row. This may be useful sometimes. You have a 0 here, but a 1 here, and you want to bring the 1 so it's the leading one in that column. You can do that. Fairly rarely used, but it's allowed. And you can scale a row. For example, here when we had the 3, we divide the whole row by 3 to get a row 1, 2. So that's it. I mean, these are things you would assume you can do with equations, so you can do them with augmented matrix as well. I will let you read the step-by-step procedure, the actual algorithm on your own, because there's no point in me just saying what's written there. It's not super exciting. This is another example. All right, so there's some interesting things going on in that, normally, for example, this system of equations, the solution is x is equal to 1, y equal to 2, z equal to 3. So when the reduced echelon form looks like this, there's a 1 and a constant on the other side. This is called a unique solution. But sometimes there'll be a whole row of zeros in the last row. Could be 2 rows of zeros here as well. And in that case, the solution space is infinite dimensional. I'll just say it here because it would take another 2 minutes to explain, and I want to get this video over quickly and get to the examples. There's another weird edge case is when you get the zeros in the last row and a non-zero here. Now think about this as an equation. It's 0 times x plus 0 times y plus 0 times z equal to C3. Now that's impossible. You can never have that. No x, x2, x3, multiplied by zeros can give a non-zero. If C3 is non-zero, then we say this equation is doesn't make sense. It's inconsistent. It doesn't have a solution. All right. Now this is really cool. Is that all these algebraic manipulations can actually be interpreted as 2-dimensional and 3-dimensional problems in geometry. So if you had an equation of a line, so this is called the general equation of a line. So this would be some line. If you have xy plane, it would be some line like that or like that, depending on the coefficients, depending on the constant. And this is a second line. So we're looking for a point xy, also in the plane, where the two lines intersect. So that's what it means graphically to solve a system of equations, is to find the unique point, or it could be non-unique, or we're looking for the point xy where it intersects. So why does this make sense? So if the point, it's like the point has to satisfy this line, right? If the xy is on the line, it satisfies this equation, and at the same time satisfy this equation. So that's why the intersection of the two lines is a special point that satisfies both equations. And even though there are many points that satisfy this equation and many points that satisfy this equation, there's only we're looking for the one that satisfies both. So that's why we're solving the system of equations as a block together. Now, there are 3 possibilities, which I don't have a graph of yet, but we'll see shortly. Either the two lines intersect. Wow, this is horrible. All right, to try to make it a little bit bigger. Either the two lines intersect. In that case, there's one solution. Or it's possible that the two lines are collinear, like one line is on top of the other. Wow, this is tricky. So if the two lines intersect, there's one point that's on both of them. If it's the same line, one line is equal to the other line, then they're sort of on top of each other. So every point on the line satisfies both equations, even though it's like one equation. So that's how you get infinitely many solutions. There's no, if you ask what is the point where the two lines intersect, it's like, well, actually, they intersect everywhere. So the whole line is a solution. All right. The third option is if the two lines are parallel. All right. So then, where do the two parallel lines intersect? Well, nowhere. Sorry. No. So there's no solution. When I say find me the point where the two lines intersect, well, no, they never intersect. So there's no solution. But you gotta keep this in mind when I say in an exercise, or you're in your teacher, or in an exam, they say find the solution. It doesn't mean there is there will be a number xy. It's really there are 3 possibilities. Either there will be one solution, like a pair xy, or there will be infinitely many, or you say there is no solution. Like you gotta keep that in mind. The same thing if you have 3 equations with 3 unknowns. These correspond to planes in R3. Now you already saw how much trouble I had mimicking lines in a plane. So with planes, it will be even harder. But yeah, so this is the case with no solution. If 2 planes are parallel, they never intersect. In 2 planes, if one, anyway, I'll let you read it. All right, which brings us to the math using SymPy. So in general, you can do row operations to solve systems of equations, which shows here. But on the computer, there's actually a shortcut. All right, let's switch to the notebook. So what's going on here is the exercises for chapter 4. We're starting off really smooth with a few simple exercises. Let's look at them here. So suppose you're given this system of equations. This is the augmented matrix, and you're asked to solve it. You're asked to find the reduced echelon form. So normally by hand, you would have to do the steps one by one. But on the computer, so let's just, I've recopied it here. On the computer, actually, you can do, so there's no vertical bar here. I mean, you have to keep the vertical bar in your mind that these are coefficients and these are constants. So on the computer, you can jump, you say, given any matrix object, you say, give me the reduced echelon form. And then you read off x equal to 4, y equal to -2. Wow, that was hard. So, by hand, you have to do the row operations. on the computer, just go RREF. Now let's look. Okay, so I mentioned there's geometric interpretation. So this is the first line, and this is the second line. I've extracted the coefficients, and now we can take a look at the two lines. So it's a bit hard to see, but this is a line with equation 3x plus 3y equal to 6, right? I mean, we started, and this is the equation. So this is what they look like, and visually we can see that right around here. All right, well, it's 4 minus 2, and x is 4, y is minus 2. The two lines intersect. So it's like a verification that, you know, our algebraic procedure gets to the right answer. Super exciting, right? Now let's do the same. So this is the same matrix, which I call A for some reason now. But let's find the RREF using row operations. So, okay, let's look here. The first thing you want to do is have a leading 1 here. When you have a 1, it's easy to subtract from the bottom rows. You don't have to think like, oh, 2/3, subtract 2/3 times this row. So that's why we want to have a 1 here. How do you get a 1 here? You divide the whole row by 3. So how do we do that? In SymPy, you say the first row, so the row with index 0 is the first row of the matrix. This is telling you that it's the whole row. And I want you to assign a third of itself. Let's see what that does. Yay, we got a leading 1 now. Next, we want to subtract this row from this row twice. This will get rid of this 2. So you literally write the second row is equal to the second row minus 2 times the first row. Do it. All right, so now we're done with this column. We look in the second column here. We want to have a 1. How would we get a 1 here is if we multiply, scale this row by minus 2. And it's done. Now we want to get rid of this 1 here. And that's the last step, is subtract 1 time this row from this row. And we're done. So that's how you do the row operations. How did I know which row operation to do exactly, and what was the procedure I was following? I was following the Gauss-Jordan elimination procedure. I won't explain it any further because we don't have time. Now, in exercise 4.3, it's very similar to the 4.1, but now we'll explore the other edge cases. So what happens here? So, oh, this is that case. So we get 0, 0, 1. So imagine this equation. It translates to this equation. Now, there are no values x and y that satisfy this. So that's why this has no solution. So the answer to A here is no solutions. We're going to repeat the visualization to see what's going on. And as you can see, the two lines are parallel. So there is never a point that will never intersect. For this, all right, so we have two leading ones. X is equal to 0, y equal to 2. So this seems to be a standard case with one solution, with a unique solution. Let's look at it. And indeed, at 0, 2, the two lines intersect. So that's your answer here. And look at the third one. So this entire row is redundant. Really, if you look at this, you actually have one equation. It looks like I've given you a system of two equations, but this this row is just 3 times this row. So in fact, you have one line. All right. So any vector that's multiple of this vector would produce, if you plug in here minus 1 times 1, 1, you get a 0. But never mind that for now. Let's see what happens geometrically. Well, there are two lines. So the first line I asked it to draw was in blue. See, I can comment that out and you see it. See, it's a blue line. And then there's a second one right on top of it. So you kind of see the blue. Well, I see it, maybe not you. So that now you have it. We have 3 cases. So this system of equations here had infinite number of solutions. This one had 1 solution. This had 0 solutions. So don't forget that. And you should probably try to do this on your own. And that's it. That's what I wanted to show in this video. I recommend you read about the Gauss-Jordan elimination procedure. It's fairly straightforward, but there's no point in me like talking about it right now when you could just read it. All right, peace out, everyone.